Thank you, Sam, for that great introduction, and just like to let's see. Here we go. So yeah, I'd just like to thank everyone here at Box for giving me this opportunity to speak today. And so this talk is about monitoring and how you can use monitoring to not have high-profile outages. So it's a complicated world out there today. We're all running a lot of complicated systems, and people are paying attention. And things go down, and people notice, and people write about it in the newspaper, and then people have a bad day. And so this is basically going to be a talk about how to not be the person having the bad day. So I'm going to kind of build this talk around a series of war stories, actual incidents that have happened, so a couple of which you might have heard of. So before I launch into that, so as Sam mentioned, I'm now at a company I founded last year called Scalar. And a little bit like what Sam was showing before, that picture with all the little boxes that you need to put together, everything from network routers on down to file servers and everything in between to do document management in a company, and now Box just kind of packages that up for you as a cloud service. That's what we're trying to do at Scalar for server monitoring. So this is not a marketing talk. I'm not going to drag you through a lot of details of our product, but the kinds of things I'm going to be talking about today are the kind of things we're trying to enable at Scalar. And the aim, just as with Box, is to really simplify the story. So take a problem that used to require a lot of separate pieces, a lot of separate tools, kind of duct taped together, and put it out there in one nice, simple cloud-based package. Okay, end of plug, on to the talk. So I'm going to dive right in with a case study. Some of you may have heard of Microsoft's Azure service. This is their equivalent of Amazon Web Services. It's basically a Windows-based cloud hosting service. It's a very large, sophisticated service. They have data centers all over the globe. At 4 p.m. on February 28th of this year, which was the moment when Greenwich Mean Time rolled over to Leap Day, a date handling bug triggered in the Azure code. And the impact of this was that no new virtual machines could launch anywhere on the Azure cloud, anywhere worldwide. No new jobs could start, existing jobs could not grow or migrate. This eventually led to a series of cascading failures that really severely impaired everything that was running on Azure. So again, this started at 4 p.m. At first, no alerts triggered, and according to Microsoft's Postmortem, no one at Azure Ops was immediately aware of the problem. After 25 minutes, the first wave of failed virtual machine launches that had encountered this bug all timed out and were automatically relaunched, but still no alerts had fired. For 50 p.m., that second wave of VM launches timed out and was retried, still no alerts firing. Finally, 75 minutes in, the third wave of VM launches timed out, and that three failures in a row triggered some other internal safety check that then started marking servers as bad. If we try again and again and we can't launch a job, maybe it's the actual computer that's at fault. And so suddenly, lots of Azure servers all over the globe were marked as bad. And this finally tripped an alert, and finally operations people started looking at the problem. That was 75 minutes after the onset, so that was 75 minutes that they lost responding to this very big and serious problem that was affecting their entire service. That's not a position you want to be in. These are the kind of stories I'm going to be trying to tell through the course of the talk, and I'll be presenting the other thing I should say, so Microsoft published a very nice postmortem, actually, of this incident. And I have to say, you read the postmortem, and they come off fairly well. This was a serious outage, but it was of that, this could happen to anyone kind of a flavor. So the lesson is not that that was a bad team. The lesson is that some of these things are hard, and monitoring in particular is hard. There can be things that slip through the cracks. So in this talk, I'm going to try to present some techniques you can use to avoid that. And so, gather around as I tell my tales of caution and woe, and hopefully learn from them. Now, as Dave Barry likes to say, I am not making this up. All these stories are true, at least to the best of my knowledge. Some of these are public, some involve inside information, so a few occasions I'm going to have to leave out some identifying details. A fair number of these stories are going to draw on my own personal experience running Rightly after we were acquired at Google. All the graphs I will show you are made up. I sketched most of them out this morning, but because I don't have the raw data, but they all reflect my best attempt to capture the flavor of things that really happened. Okay, so by the end of this talk, if I haven't already, I'll hopefully have scared you into agreeing that monitoring really is critical if you want to run a major service and keep out of the newspapers. I mean, it's really important. It's right up there with things we all know to pay attention to, like security, disaster planning, QA, internationalization. Okay, there's a long list of really important things, and I don't have actually building your product on this list. So, all right, let's take a deep breath. How do we balance all of this? And for monitoring in particular, how do we balance the desire to avoid a big outage with the desire to actually get any regular work done? So the way I like to think about this is that monitoring is basically a form of QA. So traditional QA testing is how you hopefully identify problems before they reach production. Monitoring is how you identify the problems that did reach production. But by thinking of this as part of QA, we give ourselves a framework for how to approach it. As with traditional QA, you want to you get the most coverage of your system with the least effort, and you'd prefer to find problems as early as possible, but you recognize that it's always going to be a trade-off because there's a limit to how much effort you can put into setting all this up. So the next big segment of the talk, I'm going to walk through a few different techniques you can use to get reasonable coverage at reasonable effort. So, the basic technique, this is monitoring 101. You watch out for bad things, things that you don't want to have happen. You don't want to serve error pages. You don't want your site to be slow. So you measure these bad things. You put in some kind of a threshold that if there's more than this many bad things in a certain time period, then you get alerted. We're all familiar with this, so I'm not going to say much about it, but there are a couple things that might not be so obvious. One is to think about how to get the most coverage for the amount of effort you put in. So ideally, if there's any problem anywhere in your system, you want to know about it. But if your system is big and complicated, then a sort of brute force approach to that might involve setting up enormous numbers of alerts and tuning them all and turn into a big project. There's usually a couple of bottlenecks in your system, such as the web front end, that kind of if you monitor that, you're going to be a lot of the way there. So there can be many different parts of your system where if they have a problem, it's going to show up in the web front end. Some users are going to issue a request, they're going to hit whatever back-end system or subsystem, and it's going to show up as an error there in the front. So if you just monitor for errors and slow responses and a few other basic problems like that in your web front end, you're going to get a lot of the way there. But then you need to think about that explicitly. What are you missing with that approach? So in this picture, if you can see my little red dot, imagine you're running some web service, and here's just sort of a generic schematic. You've got some services sitting behind that it depends on. But maybe one of those services, maybe you've got a back end here that's doing something that's not critical to the site, and maybe you've actually coded defensively so that if that orange back end goes down, you're not going to serve error pages. Maybe you'll serve incomplete information, or you'll have a feature disabled, but you'll keep going. So now you've made your site more robust, but you've made your monitoring less robust, because now if there's a problem in that back end and you're only monitoring the front end, you won't hear about it. So whenever you have some kind of an optional system, something where failure is tolerated, then you need to monitor those failures directly, because you're probably not going to hear about them any other way. And similarly, if you have a batch process or background code or something that's important but is not directly contributing to web pages going out the front of your site, then those are also things that you're not going to catch in your front-end monitoring, and things that you also need to be monitoring directly. So sometimes it's, I talk about monitoring bad things. Sometimes it's hard to imagine all of the bad things that you should be monitoring. So here's a real incident that happened at a major production service that I'm not going to name. So there was a piece of code in this service that would go through in the background and kind of clean out old code. And it went rogue one day, and it started just frantically deleting the entire production database, rather efficiently, in fact. And there wasn't any alert that particularly would catch that, and so data started vanishing. Users were getting incomplete results, but it didn't trigger an alert, and it was a few hours before the ops team really realized what was going on. And by that time, this very efficient cleanup process had cleaned up a pretty major fraction of the production database. They were able to save the day, but it had gotten to the point where it really took some heroics and some luck. They managed to kind of extract the data back out from some places that the cleanup process hadn't gotten to, but it was kind of touch and go. And so the lesson here is, when you're setting up your alerts, you're probably going to think about what's the most likely thing that could happen. I could have a power failure, or I could push a bad build or something. And those high probability events are definitely things you want to look at. But you also want to think about what are the things that if they happened would be especially bad. There are a lot of problems that you can fix by switching to a backup data center. You do all have backup data centers, I hope. Or rolling back a build or making some kind of a quick tweak. But if you have data loss, data corruption, there's been a security breach and someone is messing up your data, that's hard to roll back from. And so those might be low probability events, but they're high cost events. And so that's another area to spend a little time just thinking about what you could monitor there. One very simple thing I always like to do, having had a problem or two like this in my own history, is anything that destroys data, I like to put a monitor on. And if it suddenly finds a lot more data than usual that it feels it should be destroying, that's a good thing to trigger an alert on. Okay, the flip side of monitoring bad things that's less often done is to monitor good things. Users are amazingly good at noticing when something is wrong with your website, and they'll respond to that by failing to do things that normally they would do, like clicking on links, uploading files or submitting data and so forth. And if you watch for that, that can be a very great broad spectrum way of detecting problems. One example of this that was lore that I used to hear at Google is supposedly, and it's probably true, that there was a very carefully watched alert on dollars per second. Google has very good visibility into the ads that they're serving, what the bids were on those ads, so they can compute in real time exactly how much money is coming in the front door. And they watch that metric like a hawk. And if that suddenly drops, pagers will go off. And this is really a great metric to watch because it rolls up all kinds of behavior. Anything from a connectivity problem to a server bug to mistuning in the subtle algorithms that are deciding which ads to serve. Those will all show up. And because it's measuring a direct business goal, you're not going to get a lot of false positives. There are plenty of reasons why ad revenue might suddenly drop, but very few of them are things that you don't want to be bothered with. So this is a great alert. It's going to catch a lot of problems, and it's going to catch very few false positives. If the Azure team had been, had some of these metrics, for example, if they had been monitoring the rate of successful virtual machine launches, or so the rate of success at a couple of other things that might relate to that, I suspect they would have caught their problem within just a few minutes rather than 75. Because remember, that incident, it was just everything came to a screeching halt. At 3:59, things were working fine, and at 4 p.m., no virtual machines were launching anywhere in the company. If they had any kind of a metric on the normal events that come out of that, it would have immediately triggered. And so again, the best kind of metrics to use for this are business metrics that you really care about, because those are going to be fairly sensitive to a lot of different potential problems, and they're going to be the alerts that you're going to want to hear about it, where you're not going to perceive false positives. So here's a quick little case in point. Apparently on October 13th, just a few weeks ago, Oracle's homepage, that screen grab at the bottom, it's a little unclear, but this is just a little fragment I found someone had posted online. Oracle's homepage was hello world for over an hour. I saw a number of different reports about this over the internet. Now, I don't know the backstory. I don't know whether this was a security breach. I think more likely it was probably just a configuration glitch. But you would think a hacker would have more imagination than hello world. But whatever the cause, and again, there was no postmortem I saw. I don't know any backstory, but it was up there by many reports for over an hour, and you have to assume that means that Oracle did not know about it for a good fraction of that time. Now, this isn't an error page. It probably served very quickly. So, any kind of a bad thing alert you might think of probably wouldn't trip. But a lot of good things probably dipped. If you have no home page, then there are no links to click through. A lot of activity that Oracle likes to see probably dropped off. And so, a good things alert might have caught this pretty quickly. Another good technique is to monitor work in progress. So most of the logging and monitoring that we use is based off of completed operations. Your Tomcat or Apache or whatever finishes serving a web page, and then it logs both the request and the response. A lot of logging has to do with, all right, I just finished this, I just finished that. And that's fine in the steady state, because the work coming into your system equals the work going out of your system. And so these completion statistics give you a pretty good picture. But often when things are going wrong, you're not in a steady state. Things may be piling up or getting dropped on the floor, and suddenly your completion logging is not really telling you the whole story of what's going on. So, and I've had this bite me a number of times in my career. I've had plenty of cases where I get anecdotal reports, maybe from users, maybe from coworkers, that the site is locking up. Every now and then they'll try to load a page and it just spins. And so I'll go to my trusty dashboard, and it looks like this. All the lines are going pretty much straight across to the right. So I've mocked this up. This is fake data, but again, representative of real incidents. Do you see the problem here? There's a problem here. This, you'll see, and I'll peel back the curtain in a moment, but I found you'll get this kind of a graph when you have a problem where something is locking up and some of your requests are just getting stalled. It might be a particular feature or subsystem that's stuck. It might be that you're running a pool of servers and one server in the pool is stuck, but some fraction of all the work coming into your system just hangs and never completes. So here's the same simulated event. I've taken the same requests per second graph, and I've added a graph on the number of in-flight operations, requests that have come into the server and haven't gone back out yet. And so now that we know where to look, so there's that little, see that? That's where, so what I've simulated here is just something like 50 servers, and one of them hung right there. So 2% of our traffic drops out. And if you know right where to look, you can see it. But back here, that dip is still there, but you're never going to spot it. So a work in progress graph like this can really make it a lot easier to spot problems and diagnose and troubleshoot and get down to the root cause so you can fix it. Another important type of monitoring is exceptions. The great thing about exceptions from a monitoring perspective is that they carry a lot of data that you can use to categorize them. So it's a great way, it makes it much easier to automatically identify new kinds of problems. Maybe if you've got a certain amount of background noise in your system, like I've shown here where there's that errors graph down at the bottom. Even a healthy website often will be serving some small fraction of errors for all kinds of reasons. Some of them are your fault, some of them are something funny your users are doing, but there's always a little bit of background noise. But if something new pops up, you'd like to be able to identify it and And exceptions lend themselves to that because often a new problem will have a new stack trace or a new error message. This is such a useful tool that it's worth the effort to make sure that you're gathering exceptions from every part of your system. So maybe you're already doing this for anything that goes on your web front end, but you should be doing it also for background threads, which often, depending on what framework you're using, might tend to get silently swallowed and not even show up in a log. But you can go in there and add a little code to make sure background threads, backend services, JavaScript code out in the browser, any code you're running anywhere, you should really be taking the trouble to gather all the exceptions that get thrown. And there are little toolkits and things out there that can help with that. When I'm running a smaller system, I'll usually set it up to actually just send me personally an email every single time an exception is thrown. And if you stay on top of problems, and of course put a throttle in for safety, this turns out to be surprisingly practical. You'd expect the phone to be ringing off the hook, but if you're running a tight ship, it really doesn't happen. And you can always turn it off, if temporarily there's a problem. But it's a great way to really stay in touch with what's going on in your system, especially at staging and developing kind of environments and so on. You spot a lot of problems that in that low traffic staging environment, maybe they're not happening often enough to show up any other way, but if you're seeing all the exceptions, you only need it to happen once. It might have even been on a background thread where the user who was testing it didn't know there was a problem, but you find out about it before they do. On a larger system, that's not gonna work out, and so then you need some kind of automated system that can automatically flag for you when there are new exceptions or a sudden increase in the rate of an old exception. Another thing to think about is trying to detect problems before they really blossom into a production incident. And you can't always do this. Often you can't. Hypothetically, I don't know, just to make something up, let's say a hunter accidentally shoots out the fiber optic cable leading into your data center. Not that that would ever happen, not that I've ever heard of a case like that, but let's just say that happened. You're not really going to pick that up ahead of time on your monitoring. But there are some problems that you can spot in advance, especially capacity-related problems. You're starting to run out of disk space. You're starting to exceed the CPU or the RAM or bandwidth or some other constrained resource on your system. That tends not to be a sudden thing. It's a gradual creep, and then you fall over some tipping point. And it's really valuable to spot these before they blossom into a production incident because they're not necessarily problems that you can quickly correct. If traffic to your site has been gradually growing for 6 months, you can't fix that by rolling back your new build. You're going to need to add capacity, and maybe you can do that quickly, but maybe you can't, depending on where you're hosted and on how you're configured. You may be resharding databases, you may be running down to Fry's to buy a new server. There's better and worse scenarios, but it's not always the easiest thing to add new capacity. And so it's just a general principle that the earlier you find a problem, the happier you're going to be. So here's another case study. Some of you may remember that a couple of years ago in October, Foursquare had a big incident. They were down for 11 hours. And the triggering event was that one of their database shards, the working set on that shard, exceeded the available RAM in the server. And there was just no way out of the problem except to reshard the database, no way to get the site back up in the meantime. They didn't spot it until it had tipped over, and it took them 11 hours to climb out. I do have to admire the title for the blog post the next day where they postmortemed it. So that was a bummer. Another category of problem that you can sometimes, well, hopefully always in this case, spot in advance is things expiring, DNS certificates, SSL, or DNS registration, SSL certificates, things like that. There was a famous case of this way back in days of yore in 1999. There's a lot to this story, but briefly, Microsoft forgot to renew the DNS registration for Passport.com, which is their authentication service, of course. In fact, they dropped the ball so badly that some good Samaritan in Tennessee figured out the problem before they did, basically hacked into their account at Network Solution, got into the payment page, which wasn't very hard, and on his personal credit card paid their outstanding DNS bill just so he could get his email. They did eventually reimburse him, and I think they gave him a $500 little, gift card or something, but that was a few weeks later. Yeah, you don't want to be that guy. I mean, you don't want to be, Microsoft in this scenario. Maybe you want to be the other guy. But this happens. This is the most famous incident I've heard of, but it's not the only incident I heard of. So any kind of certificate or thing like this that can expire, you either want an automated system watching it, or just a recurring appointment on your calendar to check it out manually once a quarter, but something that's going to keep that ball from dropping on the floor. Okay, so in the next section of the talk, I'm going to talk, as I've kind of covered types of monitoring and approaches to monitoring. So here are some tips just for kind of continuously improving your monitoring as your system runs. So an important part of anything you do with monitoring always comes down to setting thresholds. There's always this parameter in there of, all right, this is the thing we want to pay attention to, but when does it rise to the level of something that you're going to tell me about? And this can be actually really hard to get right. And it's important. If the alert is firing all the time, it's noisy and you're going to ignore it. If you set the threshold too high, then the alert's never going to fire and it's not protecting you. So the basic technique here is to look at historical data. You want to find that Goldilocks threshold, not too high, not too low. Maybe, and you can kind of almost do this mathematically. Maybe pick a number where, based on your historical data patterns, it's going to trigger every 60 days. That might be often enough that the things it's telling you about are probably real things. Maybe you have to hunt around a little and find that manually, or hopefully your monitoring software can help you pick that number. Even better often is to have an alert, have a threshold that's parameterized. Maybe it's defined in reference to your traffic or the value from 1 week earlier. If you have a daily and a weekly pattern to your site usage, then maybe the monitoring data at any given time ought to look pretty much the way it did a week ago. And if it's way off of that, then that might be something you want to know about. If you're running a pool of machines, you could compare them to each other. If one of them is looking different than the others, then that's a good thing to know about. Or you may want to look at ratios. Look at the ratio of errors to requests, or the ratio of in-flight operations to newly arriving requests. So just a quick example of the difficulty of setting a static threshold. So say you've got a service that's got some kind of day-night variation in usage. What's the number? This is the healthy level of in-flight operations, and you want to put an alert if that spikes. Well, where are you going to put that? You've got to be somewhere above 30, or it's going to go off every day at lunchtime. And but that's 4 or 5 times the expected value at night. So now you're really not even monitoring at night. I mean, things would have to really skyrocket before you hit that alert. So that's why parameterized alert, where you're looking at comparison to old data or ratios of different metrics, really becomes important. A pretty obvious thing is you want to avoid false negatives. So that's when you have a problem and it slips past your alerts. The QA analogy is pretty clear here. If a bug slips past your testing, you add a test case. If an outage slips past your alerts, you're going to add a new alert. Sometimes you want to ask how you how you could have caught something sooner. So the Azure system did eventually flag that outage I talked about at the beginning, but it took 75 minutes because it was only when a secondary or tertiary effect kicked in that it found an alert. So how can you get back closer to the primary root cause? And so you can add new alerts. You can get more clever with your thresholding, as I talked about a little bit. Sometimes the data you would need to detect the problem just doesn't exist in your monitoring, and then you need to add, sometimes you can add a couple lines of code to your system, log some new metric, and then that'll give you the data you need. If you have a really bad outage that got past your monitoring, then you want to think about defense in depth. Add 2 or 3 or 4 different alerts which would all catch that problem from different directions. I like to think of this as getting full value from your crisis. If you're going to go to all the trouble of having a major production outage, then you should at least get your money's worth in terms of lessons learned. So that was false negatives. It's also important to take care of false positives. If you have an alert that's firing all the time, that's like a flaky test, you're going to start ignoring it. You might even start ignoring some of your other alerts, maybe accidentally. And so, there you may just need to tune something, adjust your threshold again. You may need to look for a better metric to monitor, something that more directly measures bad behavior you really want to know about. But also a noisy alert might not really be telling you that you have bad monitoring. It might be telling you that you do have problems with your actual production system. Maybe the alert is going off and it's because of something that didn't really cause an outage, but it could tip over the edge to a more serious problem down the road. And so it's a good time to just assess a little bit and say, is it okay that this metric is noisy and is spiking every now and then? Is that hinting at some deeper problem that I should investigate? Okay, for my next section, so far we've focused on alerting, which is making sure that if there's a problem, you'll know about the problem. The other aspect of monitoring is troubleshooting, digging down, once there is a problem, digging down to the root cause so you can fix it. These are very distinct activities. They involve the same data often, but really working with it in different ways. Now, actually, troubleshooting is a huge topic of its own, could cover several additional talks. But what I'm going to focus on a little bit here is the monitoring side of it, how you can structure your monitoring data so that when you are in a troubleshooting situation, you'll have a better chance at finding the problem. So first thing that people don't always think about is it's important to really understand your monitoring data. If you actually map out the whole sequence of events from maybe a user requesting a page on your site to the little tiny uptick on a monitoring graph somewhere, it can be a pretty long chain of events, and so there's a lot of opportunities for artifacts to creep in. That data you're looking at on your graph has probably been time bucketed, averaged, there may be smoothing or subsampling going on. And that's when everything's working well. If you have a production problem, it may be affecting your monitoring as well. Some data may be getting lost, maybe getting double reported, or who knows what's going on. And so when you're looking at a graph and struggling to make sense of what it means, it's very important to know, how the sausage got made. What were the chain of events that produced this graph? Because if there's something wrong in the data, and that can happen, your only hope of understanding that is if you understood how the graph is being put together. So here's a simple example. In the early days of our migration onto Google infrastructure at Rightly, my pager would go off a lot, and it was saying that the site latency had spiked. And I would go pull up the dashboard, and sure enough, I'd see a latency graph that looked like this. Now, I couldn't see any problem. Users weren't reporting problems, but the monitoring system was very insistent that we had a latency spike. An investigation, it turned out that every now and then, we'd have a single request that would come into the system, and it would take hours to process for some mysterious reason. So, in the morning, someone tried to load a web page, and that evening, the web server finally came back with, oh, here's your page. Now, the browser had long since gotten bored and wandered off. But the server didn't know that, and very happily and proudly deposited a record in the log saying, this request completed, status code 200, so many response bytes, elapsed time 53 million milliseconds. 53 million is a big number, and when you drop that into a 1-minute monitoring bucket and swirl it around in the average with all the other little 13 millisecond requests that finished in that same minute, it blows the curve a little bit. And it so happened that we were using a 10-minute running average in our graphs, and so we got a nice 10-minute wide square wave in our graph. And once I figured out where that was coming from, I was a lot happier. A little unhappy that there were these mysterious 8-hour requests going on, but happy to know that it wasn't a big problem. So kind of the underlying lesson there is that we rely on averages a lot in our monitoring, and averages can hide a lot of important information. So here, for example, is a graph that's showing the mean latency for a hypothetical service running on a pool of 40 web front ends. And this is another, one of these simulated scenarios I put together based on things I've seen in real life. And so I've inserted a simulated problem. It's a non-trivial problem. You probably can't spot it here. So remember again, this is the mean latency. This service is having a performance problem, and here we're looking at the mean latency across the entire front-end server pool. Here's the same data, but now I've broken it out by individual servers. So it's kind of all swirled together there in the middle, but there are 40 different lines here representing our 40 servers. And what's happened, and this is something that really happened on Rayleigh, is that every now and then one of the servers would tip over into a state where it got a lot slower. The specific root cause was that we were using regular expressions to process some user data, and there was a certain pathological input that would cause the regular expression to basically run forever. It was exponential in the length of the input. And so basically, from then on, whichever server that it happened to was running with one core tied behind its back, because it was just furiously trying to crunch through this bad regular expression. And any requests then that landed on that server, they were sharing time with the regular expression processor, and they ran a lot slower. But it was a rare case that would tickle this, so it was only affecting a server here and there. It never caused, nothing we ever noticed on our dashboards, nothing our monitoring ever reported. But it was probably slowing the site down overall by about 5%. And that's kind of a big deal. I mean, think about how much work you would be happy to go do on some kind of optimization project to speed your site up by 5%. So the lesson is you need to sometimes get past averages to really understand what's going on. And from an alerting perspective, differential monitoring, comparing servers against one another, it would be a great, that would have flagged this right away. For troubleshooting, you need to, drill down past this kind of a graph and break things out by different servers, different features or requests, or whatever the kind of the axes of your system are. And if your monitoring system can show you, these kind of breakout graphs, or maybe a top-end report of, which are the 5 slowest servers, things like that, those can be great tools to track this kind of thing down. Another important lesson for troubleshooting is, so many problems come down to some kind of a resource constraint. You're using too much CPU, too much bandwidth, RAM, whatever. And often it's a small fraction of your traffic that's driving that. And subtle shifts in that fraction of expensive traffic can cause big problems. If you don't have in your monitoring detailed information about how much resource each request or each operation is consuming, you're going to have a hard time tracking down these problems. So we tend to monitor counts of things. How many times does this happen? But we often don't monitor how much did each of those things cost, how much CPU or bandwidth or other metric did it consume. So here's another case study. This is a system that was storing documents. Documents were associated with different users. And this particular system was responsible for supporting text search over these documents. And the way the system was architected, so there was an index for each user. When user 1 does a search, we look in user 1's index. So every document that user 1 has access to will have a copy in that index. That could be their private documents, or it could be a shared document that they're one of the collaborators on. And so this is what the expected kind of performance and cost of the system was supposed to be. Most documents were pretty small, say on the order of 10K. Most documents were private. The ones that weren't were maybe shared to 1 or 2 other people, sometimes a lot more, but rarely enough that the average sharing was maybe something like 1.2 users per document, including the owner. And most documents don't change very often. If you consider over their whole lifetime, which could be years, per day over that long lifetime, they almost never change. And so if you multiply this together, average document size 10K, average sharing factor, which means the average number of indexes that the document's going to appear in, of 1.2, and maybe it changes 0.2 times per day. So the indexing cost for that document, on average, is expected to be about 2.4 kilobytes per day. Really nothing. But it turns out that these three parameters, size, sharing factor, and change rate, correlated. And so the mean of the products was not the product of the means, which is to say there were some outlier documents that happened to be rather larger, say half a megabyte, sometimes had thousands of users that they were shared to, and changed a lot more often. And when you multiply all that together, you'll find a document like this, instead of having an indexing load of about 2.4 kilobytes per day, it'll be more like 250 gigabytes per day. It's 100 million times more expensive than had originally been projected in the system design. Oh, but wait, there's more. These documents were so crushing the back end so hard that often indexing updates would fail and be retried. Quite a few. In fact, it was typical that they would be retried. It could be half a dozen times. Which was another factor of 5 or 6 on the cost, because there'd be all this wasted work before we finally have the successful index update. So now we're up to, and you know, I'm making this number up, but it's kind of the flavor of what was going on. You know, maybe a terabyte per day per document for the small number of documents that had this kind of behavior. After months of investigation of why the indexing system was using up so many resources, it finally developed that a fraction of a percent of the documents in the system were the majority of the indexing cost, and the indexer was the most expensive component of the entire system. So the lesson here is that the long tail, whether it's of documents or users or any kind of thing in your system, the long tail can kill you, and if you're not gathering data that shows you the costs of different operations that are going on, then you're going to have a very hard time figuring out why. So I'm running a little long. I've got just one more segment, so I'm going to go through this pretty quickly. You know, something that tends to come up a lot in troubleshooting is untangling cause and effect. Your pager goes off, you bring up your dashboard, and all the graphs are swinging wildly. Latency is up, database traffic is up, site traffic is down, everything's going in one direction or another. And most of this is going to be secondary effects and distractions from the real problem that you need to be finding and fixing. So here's a little example I've cooked up. And with all the examples, it looks like something that I've actually seen. So, you know, we've got a problem on our website, and we're looking at our graphs, and we see that CPU usage has spiked and site latency has spiked. And so it's pretty clear that something is getting more expensive. We're needing more CPU for each request, and or maybe there's just more requests using more CPU. And because the CPU is overloaded, the site is slowing down. Well, that could be. You know, there are plenty of times you'll have a problem, and that will really be the story. But let's imagine it was like this. Let's break out that CPU usage into the application code, which is kind of steady, and the garbage collection, which is just skyrocketed. And the reason for that in this scenario is that our database server or some other back end has slowed down. Maybe we're running a batch job that's pounding on the database, or hypothetically, maybe it's halftime at the World Cup, and Brazil is playing, and everyone in Brazil is taking advantage of halftime to run to their computer to talk about the game, mostly on a certain social network that happened to be very popular in that country at the time. And maybe you're sharing a data center with that social network, and a backbone network with that social network. You know, I'm just saying. So, there's this problem behind your web front end. It's slowing things down. So requests come into the web front end. The front end's working fine, but it's waiting on the database. And so there are more in-flight operations on the web server, which are taking, there's more threads, more ephemeral state, a fuller heap. And so now suddenly your garbage collector starts to kill you. Now, so now cause and effect are exactly reversed. The latency problem was the root cause. Well, under that was the deeper root cause of the database. But within the web front end, the latency problem was causing the CPU problem, and not the other way around. So it just illustrates how difficult cause and effect can be. There's no magic bullet to solving this. But if you just kind of think back to basics and think about the scientific method, that can help a lot. And what I mean by that is, when you're trying to explain to yourself what's going on, you want to have a clear hypothesis. The database is overloaded, or this failed, or you come up with some hypothesis, and then you really look through your graphs a little bit, and you say, does this hypothesis explain these graphs? And if the answer is no, then maybe you need a new hypothesis. But when you're running, a larger system can actually be easier in this regard because you have different vantage points, different systems to look at to get different views on your problem. If you've got a database that you're suspecting and you've got a number of different services that are depending on that database, then you can look at the different services, and if they're all having trouble, then that supports the idea that it's the database that's at fault. If you don't have multiple systems using your database, or you've got some other back-end system that only has one customer, it's often a nice idea to create an artificial second customer. Just a little program that just sits there and sends a little trickle of requests to your database or your other back-end system. The nice thing about that is it's very predictable. So if this fake customer, you monitor that, and if suddenly that starts seeing different behavior, you know it didn't change because you never touch it, and it's always doing the same thing. So if its behavior changes, it's because the back end that's behind it is having some kind of a problem. All right, so that's the end of the prepared notes. Again, thank you all for coming. I'll be here for a while. I'll be up here to take questions on the mic. I guess here we have another mic. I don't know if we have a plan for. We have a plan. So if if you have a question, feel free, and I'll be hanging around a little bit afterwards. And you can always reach me at the address up here, steve@scalar.com.